The speed of light, c, is one of the fundamental constants of physics. A knowledge of its value is important in optics, where it is associated with the index of refraction. In the theory of electricity and magnetism, where it is connected with the permeability and permittivity of space. In relativity, where it enters into the relation between mass and velocity. Or in atomic physics, where it appears in Einstein's famous equation. The first successful terrestrial measurement of the speed of light was made by a French physicist, Fizeau, in 1849. Fizeau focused the light from a source onto open space between two adjacent of a slotted wheel by reflecting it from a plate of clear glass. The light was rendered parallel by a lens and then proceeded to a distant lens. There it formed an image on a mirror, and after reflection from this mirror, the light retraced its path back to the wheel, passed through the plate of glass, and formed an image in a telescope. When the wheel was set in rapid rotation, the light from the source was chopped up into a succession of wave trains. Let us observe this in slow motion. If a wave train goes to the distant mirror, and on its return is blocked by a tooth on the wheel, no light is reflected to the telescope. If, however, the wheel rotates from one slot to the next, while the light goes to the distant mirror and back, then an image will be observed in the telescope. The time t the wheel takes to rotate from one slot to the next is equal to the time the light takes to go to the distant mirror and back. If the distance between the wheel and the mirror is d, and the time to go twice this distance is t, then the speed of light, c, is equal to 2d over t. In the Foucault method, the wheel was replaced by a rotating mirror. Only during the short time interval while the mirror is in this position can the light from the source reach the lens. A moment before and a moment later, the light misses the lens. If the mirror remains stationary at this position, the light proceeds through the lens and thence to a very distant lens-mirror combination, from which it is reflected back to the rotating mirror. There the reflected light forms an image, I. However, if the mirror has rotated to this position, while the light goes to the distant mirror and back, an image I prime is formed at a position displaced from I. Thus, the rotating mirror breaks up the light into wave trains, which on their return form a new image, I prime. The displacement I prime, along with the rotational speed of the revolving mirror and the distance between the mirrors, provides the means for calculating the speed of light. Mickelson improved upon Foucault's method by using a revolving many-sided mirror, and instead of measuring the displacement of the final image, Mickelson varied the speed of the mirror until there was no displacement. We shall consider the behavior of an 8-sided mirror. Light from a source is reflected to a distant mirror. The returning light is reflected by the 8-sided mirror to a measuring point in a telescope. When the mirror is set in rotation, the light will arrive at the measuring point only if the mirror makes exactly 1/8 of a revolution in the time it takes the light to go to the distant mirror and back. If the mirror does not make exactly 1/8 of a revolution in the time it takes the light to go to the distant mirror and back, the light will not arrive at the measuring point. Only at the proper mirror speed will the image be at the required position. In the measurements of Mickelson, the distance between the mirrors was that between Mount Wilson and Mount San Antonio in California, a distance of 22 miles. As a result of Mickelson's measurements and those of other experimenters, the speed of light is found to be 2.99773 times 10 to the 10th centimeters per second. In round numbers, we may use the value 3 times 10 to the 10th centimeters per second, or 186,000 miles per second.